Okay, yeah, it's 12 o'clock, so let's start. So welcome to TCS Plus. Today's speaker is Bo Waggoner. Before the talk, let's go around the table and introduce all the groups. So first we have Abertanu Datta from Northwestern.
Hey. Abhitan is not here, but hi from Northwestern.
Okay, then we have Klamakanon from Columbia. Dimitris Paparas from Wisconsin. We can't see you, but okay. Then we have Gregory. Oh, sorry. We have Gregory from Indiana. K. Gopalkrishnan from East Carolina. Piyush Srivastav and Piyush Srivastav from Caltech. Then we have Saina Shehan from Michigan. Then we have Yu Cheng from USC. Hello. And so that's the group. Okay, so before we begin the talk, the usual stuff. You will be muted during the talk. Oops, sorry. Let me change it. Okay. So yeah, the audience will remain muted during the talk. But if you have questions, please unmute yourselves. And we encourage questions. The next talk is by Mark Zandri, and 2 weeks from now, and 2 weeks from then, it will be Jerry Lee. And for TCS Plus, behind the scenes, we have Oded Regev, Thomas Vidic, G. Kamat, and Clement Canon helping with the operations. So today's speaker is Bo Waggoner. Bo is at UPenn. He's a postdoc at UPenn, and he graduated from Harvard. And he will be talking about informational substitutes today. So welcome to the talk, Bo.
Great. Yeah, thanks very much. Is the sound okay? So this will be about my volume. And yeah, definitely please feel free to unmute yourself, stop me, ask questions. I know there'll be a slight delay, but yeah, I'm really looking forward to talking over this TCS Plus. I think it's really cool. Let's see. Okay, so I want to start with an apology that this paper is actually not yet up on arXiv. It's still being edited to be put up, and I'm hoping to finish that off really soon. Okay, so I don't know most of you. I was putting this talk together in view of a theory audience that's not necessarily very familiar with game theory, with economics, and with these signaling type of questions. So if that describes you well, then this talk is mostly aimed at you, but hopefully game theory people will find it interesting. So I want to talk about this sort of idea of value of information and use it to propose definitions of substitutes and complements for information, and then argue that they're useful at least in the theory of prediction markets and also in this algorithmic question of information acquisition. And so, yeah, so I'm going to be focusing more on this background and these ideas that aren't necessarily ours, but we're kind of synthesizing together. And I really think of this paper as synthesizing a lot of references. I'm going to try to paste them into the chat. Let's see how that works. Okay, it's formatted very badly, but that way, so I'm going to be talking about some of these papers, and I think all of these papers are sort of crucial for us to bring them together. So kind of a lot of different references brought together, and I'll be talking about a lot of that background. And feel free to stop me, of course. Okay. Okay, great. So the title of the paper is Informational Substitutes. So let me tell you what I'm thinking of when I say information. So I'm thinking of a bunch of random variables that are drawn together jointly from a prior, and I'm thinking of the case where we know this prior. So they're all drawn, and I really just care about X. I care about the outcome of X. So for example, it could be the weather. And the other random variables, I'm going to call them signals. I'm thinking of them as conveying information to me about X, right? Because they're correlated with X. So for example, X could have 3 possible outcomes, which could be sun, clouds, and rain. And these Ys could be a weather prediction from one weather forecaster. They could be a barometer reading, and so on. Okay. Okay, so that's my basic setup for information. What are substitutes? So intuitively, the idea of substitutes is diminishing marginal value. So we'll say that a set of things are substitutes intuitively if the more I have of the others, the less valuable this thing becomes to me. So I'm thinking of examples of substitutes of chocolate ice cream and chocolate bars. They're both valuable, but the more ice cream I have, the less my value for bars becomes. And substitutes have been really effective in economics, at least in my opinion, for characterizing even existence of things like market equilibria. So when is it the case that there are equilibria where everyone buys and sells their goods and it's stable? Also in stable matchings of, for example, doctors to hospitals, you see substitutes come up as characterizing existence of good solutions. And in computer science and algorithms, at least when you model substitutes with submodularity, they're very important to algorithms and becoming a very large field of study. So we have efficient approximations for many problems when the items are assumed to be substitutes. So an example, if you haven't seen this, I'm referring to submodular maximization. An example of such problem is there are n items out there, but you're restricted to only select k of those. And you have some value function that for every set of items tells you how valuable it is and which k should you select. So in general, this could be very hard because there are 2 to the n possible subsets to look over and still exponentially many of size k. But if your items are substitutes in this sense, we have efficient approximation algorithms. So this kind of raises an ambitious question of could we define substitutes for pieces of information, and would it have similar applications? And in this paper, we're hoping to argue that this seems possible, or at least that this seems like a research direction worth pursuing. And whether it will come to be the case as substitutes are for items will take a lot more research, but we'll see. So, sorry, let me back up for a second. I think intuitively it makes perfect sense where you could say, all right, I have 2 pieces of information, such as 2 readings about the weather, and they're substitutes because once I know this piece of information is not so useful to me. Right? And that seems very intuitive. So I want to mention some intuitive challenges that could come up if you try to formalize and write down a definition of substitutes of information. Okay, so first of all, for items, we assume that we're just handed some valuation function, which takes in a subset of items, let's say, and returns the utility or the value for that subset. But for pieces of information, it's not a priori clear what their value should be. So why is this information valuable? Are you curious and you want to know it, and this is encoding your curiosity? Or are you going to use this information for a purpose? Okay, for items, the value for one item doesn't have to depend on the value for another. It's perfectly valid to just take some utility function with arbitrary relationships between the values for 2 different items. But different pieces of information, especially when I model them in this probabilistic way, they could be correlated, right? They could have some constraints about what one piece of information tells you about another. And so it doesn't seem right that there could be this arbitrary value for one and for the other. It seems like this should constrain things. And for items, I mentioned diminishing marginal value. It's kind of straightforward to see what that means for items. But for information, defining a marginal piece of information is even not a priori obvious, let alone a sort of diminishing marginal information or marginal value. Okay. So this leads to a story about value of information. Okay, and so in the next part, I want to tell you about this theory of value of information and how we're going to use that to think about how much information some y gives me about some x. Okay. And then also, how can we make this theory tractable for us? Okay. Does that sound good so far? Okay, let's keep going. It's good. So the first question to ask could be, well, Shannon gave us a very nice way to measure information, right? Why not use that? So here's an example of Shannon's binary entropy function for an x, which is x is binary, so x is either 0 or 1, and on the x-axis I've plotted the probability of x. And this blue curve is the entropy of x if it is 1 with that probability. So for, and yeah, I think that's the right units. I may have shifted the y-axis, but good. So if my prior on x is that x has a probability half of being 1, its entropy is up here. And now imagine that you see some signal y, and you update to a posterior on x based on that signal. Okay, so maybe in one case, y moves you to this posterior of 0.8, probability 0.8 that x is 1. In this case, the entropy is lower. All right, and if you saw y as being a different outcome, maybe you would have updated to this posterior. And again, in this example, you'd have a lower entropy. And so on average, conditioned on y, the entropy of x is lower. And this black bar, you could argue, is a very nice measure of how much information y conveys about x. Okay, with me so far? Is this plot okay? I'm going to return to the plot. Good. Okay, so why might this not be satisfactory? I'll just give a very extreme example where maybe I shouldn't have said does not apply, but is not so useful. So here x is the event that it rains or doesn't rain, and y is some useful forecast. And imagine that, you know, I really hate carrying my umbrella to work every day, but if it rains on me, I'm going to melt and die. Okay. In this case, it's not very useful to me to get some forecast that decreases the entropy of x, because as long as there's some chance of rain, I have to take my umbrella. Okay, so all x's, all pieces of information about x where x has an entropy that's non-zero is just useless to me. I have to take my umbrella. Okay, so such forecasts that don't give me an exact outcome, will it rain or not, they're all equally useless, and Shannon's entropy is not measuring that correctly. Okay, so I'm not sure if that was convincing to you or not, but there's a paper written that sort of argued, okay, we should measure information by the value that it imparts to the choices we make, how well it can let us make better choices. Okay, and that was Howard in 1966, Value of Information Theory. And he posited this setup, which is super general. So we have a known prior distribution on x, and then an agent who's going to have to make some decision. Let's just say take the umbrella or not. And simultaneously, x is drawn from that prior. Okay, in this case, there are 3 outcomes for x. It could be rainy, cloudy but no rain, or sun. And the decision maker will get some utility that depends on the decision they took and the outcome. So the utility of the umbrella and sun could be pretty low. Utility of no umbrella and rain could be very low, and so on. Okay, and now we'll define this value function v to be the expected utility for participating in this process. And I've written v of empty set because this agent is getting no signals in the setup I've drawn for you before acting. All they know is the prior. And I'll change that on the next slide. So for now, they get no signals, and they'll have some expected utility for this process. And I want to emphasize that we're assuming here that they decide optimally. So in this case, they have no signals. So based on the prior, what decision maximizes expected utility, they're going to take that decision. Okay? Clear so far? Sounds good. Okay. So now what if they do get a signal? So for example, they get the signal y. So they look at the weather forecast when they wake up. Then in this case, they can Bayesian update to some posterior on x, which I'm calling p sub y. And that will enable them to make better decisions in general. So for example, if they don't mind a small chance of getting rained on, and the weather forecaster says very likely no rain, they'll choose not to take their umbrella. Okay, so again, based on PY, they'll make some optimal decision, and their overall expected utility for this process is now denoted V of capital Y. Because they got the single signal, capital Y, and then they got to act. And this will be a higher expected utility because they have more information on which to act. Okay, and so this is this was sort of Howard's definition of the value of information. You can also think now about the marginal value of information with this, right? So what's the marginal value of Y, or how much extra utility did the decision maker get by observing Y? And it's V of Y minus V of empty set. Because V of empty set is what they would have gotten if they didn't observe Y and they just had to make the best decision with no information. V of Y is what they get after observing Y. Is this clear so far?
Yeah.
Question? Or okay, clear. Okay. Good. Okay, so Eling and I really like this as a sort of starting point where, okay, this is what information's value is. This is how we define it. And it can apply to, this is actually a very general model, I think. But it's not super clear how tractable this definition is. So how are we going to actually be able to work with this in some scenarios or prove general things about this? And to do that, I want to introduce the next step. Yeah, so the next step of the story, which is to use ideas from proper scoring rules. Okay, so what are proper scoring rules? I've shown you here the first paper written about them in 1950, which was a paper about getting weather forecasters to be more truthful or honest in their predictions of weather. And the problem, according to Breyer anyway, is that the ways that people were using to evaluate forecasts had bad incentives. So, you know, and it's not very clear, right? If someone tells you, the weather person tells you it's likely to rain and then it doesn't rain, was that a bad forecast or did they get unlucky? How should you score such a thing? Okay, so Breyer was looking at the following setup, and this was then generalized by McCarthy, and then Savage wrote this sort of definitive paper. So I'm casting it in the same framework as Howard's paper, where there's a decision maker who has to make a decision. And in this case, their decision is to predict the weather, commit to some prediction. And here, by prediction, I mean a probability distribution over the possible outcomes. Okay? And then the weather event will happen, and then they're going to get scored with a scoring rule. Some score function that takes their prediction and the outcome and returns some utility, some score. Okay. And the idea of a proper scoring rule is one where the optimal prediction they should make is their true belief over the weather. So if they really believe it's 30% chance of sun and 40% chance of rain and so on, they should really report that and not any other probability. Okay, and so I hope that makes sense as a general goal. That maybe is something that weather forecasters wanted to do, but also a very general question, right? When can we get an agent to truthfully predict an event? By giving us a distribution over the outcomes of that event. Okay, so for what functions S is this truthful, if any? Okay, well, here's one. Okay, so this is called the log scoring rule, and it's very simple. Q of X is the probability that they assigned to the outcome X that occurred. So for example, if it ended up raining and they said 30% chance of rain, this scoring rule would pay them log of 0.3. Okay, and this is actually truthful, which is pretty cool. So formally what I mean by that is that if you believe that X is drawn from a distribution P, okay, and you want to maximize your expected score, then you should report that distribution P. Okay, Is that okay so far? Example of a proper scoring rule.
Can you give an can you give an example where it's there is no incentive to report truthfully?
Yeah. Okay. So maybe this isn't realistic, but I could just say, take whichever event you predicted as the highest probability, and if that happens, I'll give you $1. But if it doesn't happen, I'll give you nothing. Which that's a reasonably dumb thing. Okay, here's a better one. Let's say there's a binary event. So let's just say rain, no rain, and you tell me the probability of rain. Then instead of log Q of X, maybe I'll just pay you Q of X. So if it rained and you said 0.8 probability, I'll pay you 0.8. If it did not rain and you said 0.8 probability of rain, I'll pay you 0.2 because you assigned a probability 0.2 to the event of no rain. Okay, that will not be truthful. You don't I think you maximize expected score by either saying like 1-0 or 0-1, like either 100% chance one way or 100 the other. It's probably the best thing. Yeah. So the general, yes. So okay. So the general characterization says that scoring rules all have this special property that they correspond to convex functions in an interesting way, which is that the expected utility an agent faces is always convex as the function of their true belief. So here I've again gone to this event that will either happen or not, like rain or no rain. And the probability that it happens is on my x-axis, horizontal axis. Okay, and what this says is, so this is the log scoring rules curve. And it says that if an agent has true belief of 0.5, we know this is proper, so they should report 0.5. But they're going to get a pretty low expected utility. Why is that? Well, actually, either way it goes, they'll get log of 0.5. If it rains, they predicted a half probability of rain, they'll get log of 0.5. If it doesn't rain, they predicted a half probability of that, so they get log of 0.5. Whereas, for example, if someone held this extreme belief, so they knew for sure that it was not going to rain, then they expect to get, then they'll report, probability 0 of rain, and they expect to get 1. Okay, and in between here is everyone's, so if you have your true belief 0.8, your best thing to do is actually report 0.8, and you expect to get some moderate payoff. And this function is always convex for proper scoring rule. And let me check the time. So I could try to sketch, and if people find this mystifying, I can try to sketch an idea of why it's true. Again, this is background that's not directly in our paper, but I think it's like very nice to try to tell the theory community about it. So if you have any way of giving me feedback about if you'd like to see a little more about this. If anyone feels particularly strongly.
If it's a quick sketch, I think that will be great.
Okay, because I kind of wanted to try drawing on my window anyway, so this is a good excuse to do that. Okay, I'll give you a sketch that may go a little too quickly, but will give some idea of intuition, and then when you read later, maybe it'll inspire you to read later. Okay, so I'm going to draw the same plot. How's this for darkness? Well, no, let me draw it higher. Good. Okay, so for any particular report you make, let's say you make report 0.5. If the event doesn't happen, you'll get log of 0.5. And if it does happen, you get log of 0.5. So if you think about any belief you might have, what's your expected score? Well, it's always that same number. Okay, and so this line is saying, okay, if I have true belief 0.2, what do I expect to get when I report 0.5? Sorry, can you see this well? No, you can't, can you?
It's not particularly visible.
Seems to depend on light. That you guys can't see that well? It looks okay for me, but then it whites out. There we go. How's that?
That's better.
Okay. Good. So for any belief you have, your expected score is the probability that happens times that score, and the probability it doesn't happen times the other score. Okay, so for any particular report, you get a line where for that report, this line is plotting your expected score. So if I believe 0.8 with probability 0.8, I get this score if I make that report. With probably 0.2, I get that score. And so my expected score is a point on this line. And when you keep doing this, you should always make the report that maximizes your expected score. So you're always going to be reporting a pointwise maximum of a bunch of lines. And you get a convex function. And furthermore, for truthfulness, it says that you know, if you believe 0.8, the highest line had better be the 0.8 line. And that way you're truthful. So it actually touches the convex function at 0.8. Okay, so that's, yeah, so that it's okay not to have followed that because it's worth more time, but I can tell you at the end where to read more on such fun theorems. Cool. And Savage's idea, or point, well, this idea is even older, but the point is that you can actually go the other way too. So if you give me a convex function that maps a probability distribution on X to the reals, then Savage said I can construct a proper scoring rule from it by taking sort of tangent lines. So the drawing I gave to you, you kind of do in reverse. You start with a convex function, and you take these tangent lines, and I can use these to construct a proper scoring rule from any convex function. Sorry, Clement asks, this graph is shifted by 1, and that's correct. Right, so the log is actually negative, like log of 0.5 is negative, and so I shifted everything up to make these positive. Sorry about that. Yeah. And you can do that without affecting the truthfulness properties. Okay, cool. So I was originally talking about decision problems, and then I sort of specialized down to scoring rules, right? Which is a very special case of a decision problem where you report your belief. Okay, but the key idea, which is kind of present in Savage, but he doesn't develop it, is that this applies to decision problems as well. So for example, so this decision problem, right, is predicting when your utility will be a log scoring rule. But for any decision problem, you'll get such a convex function. And now let me explain these dots that just appeared on the graph. Okay, so this is showing the marginal value of information, right? So if you had a prior belief about X and you had to make your decision, your prediction right away, this is the expected score you would get, right? You would make it truthfully based on your prior belief. But if you got to observe Y first, you would update to some posterior depending on what Y was. If your updated posterior is here, you would expect to, on average, get this score. And if your updated posterior is down here, you'd expect on average to get this score. Okay, so your expected score, your expected utility in this decision problem is higher by this black line. And so that's the marginal value of Y. So here I'm just drawing Howard's definition. But the key point is that for all decision problems, the expected utility will look like this convex function of beliefs. And so for all decision problems, I can draw Howard's marginal value of information as this, by drawing the posteriors and drawing these expected scores. And this is sort of actually a Jensen inequality gap, actually, because of the convex function. So that's the key idea that makes this a bit more tractable. Okay, so while you're thinking if you have questions for me at this stage, my summation so far is we have a sort of general value of information definition. And we even can sort of get marginal value of information from this definition. We also have a way to deal with it sort of tractably, both for intuition, which is very important to me, being able to draw the intuition, and also mathematically, because we know that the analysis of these things really comes down to analyzing convex functions of probability distributions, which I really like because it's a broad class, but it's much more tractable. Okay, no one's come up with any questions, so let's go on to some definitions of substitutes and complements. So the setup we're going to have is there's a single agent, and they have a decision problem that they're facing, which I defined for you earlier with Howard's paper. So they have to make some choice, and nature is going to make some simultaneous choice, and then they'll get some utility. Okay, and now when our pieces of information, these y's, signal yi's, substitutes or complements. Okay, so here's a first definition. We'll say that they're substitutes if this value function is submodular, meaning that, okay, I have sets of signals, and I'm going to consider adding a signal yi and see how much marginal value it gives me. Okay, over here, I'm adding it to some smaller set, and it's giving me this marginal value. And on the other side of the inequality, I'm adding it to a larger set, and I'm getting less marginal value. So on the right side, I know more. I know B, which is strictly more, and I get diminishing marginal value. If I know less, then I get more marginal value. Okay. So hopefully, if the preceding parts made sense to you and you believe in our definition of the value of information, maybe this is simple or obvious, but that's good. I hope so. And if you've seen submodularity before, maybe it's not too surprising. But if it's going too fast, stop me. I kind of tend to assume people have seen definitions of submodularity. Okay, so our definition of complements will be the same, except we're going to use supermodularity, which is increasing marginal value. And so the most extreme example of complements to keep in mind is if I want to predict a binary x, like x is either 0 or 1, and I have two signals y, y1, y2, that are independent bits, and x is the XOR of those two bits. Okay, then knowing one of the bits will not help me at all in predicting x. Right, so in anything I want to do involving x, the value of one bit alone is no good, not useful at all. Whereas if I know both bits, I exactly know x, and so my value will always be better. So that's an extreme complements case. Not very realistic, maybe for an economic scenario, but good. Okay, so yeah, so this is a nice start, but in a game theoretic scenario, this is not going to be good enough. Oh, I'm sorry. Let me draw it for you on the plot, because I claimed that these plots are useful for intuition. So let's see if I can back that up now. So this is the plot I showed you before, and so let's assume that we have two signals, y1 and y2, which are IID conditioned on x, and I've drawn you these red posteriors for one of the yi's. So if I observe a yi equals 1, then my posterior on x moves up to 0.8. And if I observe yi equals 0, then my posterior on x moves down here. So some distribution where it looks like this. And now let's look at observing a second signal. Okay. Now, in purple, I've drawn various posteriors conditioned on observing both yi's. So on the far left, this could be if both yi's are 0, then my posterior on x is that it's very likely to be 0. If if they're symmetric, then this, like one yi being 0 and the other being 1, should probably be right at the prior. But you can imagine if the first yi is 0 and the second is 1, you have some posterior, and in a flipped case, you have some other posterior. But so when I drew this, I guess I didn't have these exactly IID. So I apologize about that. Okay. But again, the purple dots are different posteriors you might have after observing 2 signals. Okay, and so if I start at observing the first signal, and let's say it was a 1, so I'm over here, then the second signal will move me to one of these 2 posteriors. And so my average expected utility for playing this game, this prediction game, goes up to this point, which is just above the red dot. It's the average of the 2. Okay, and now if I take the average of all the posteriors conditioned on observing two signals, that's even better than observing 1 signal. Right, the expected utility for observing 2 signals is higher, but it's not that much higher in the drawing I just drew. The first signal had high marginal value. The second signal has relatively lower marginal value. Okay. In this particular decision problem. You might ask, if I take the same exact signal structure with the same prior and the same signals and the same x, maybe there's some other decision problem which is going to be represented by a differently shaped convex function for which it's not diminishing marginal returns anymore, marginal value. And you might be able to think of how to construct one. I'm hoping to talk about it at the end if I have time. But so that's why I claim these are helpful for intuition. And this is an intuition of what substitutes look like. For complements, the first signal wouldn't help you much, but then as you moved out, as you got a second signal, you would get much better beliefs and your value would go way up, roughly. Okay, so far? Okay, so I reference a problem here that in a game theoretic scenario, this definition won't be good enough. And here's the reason: that information can be divided up by agents who hold it and partially revealed. Okay, and I like this quote by Benjamin Franklin to illustrate that. And I tried to draw this by an agent telling another only the square-shaped piece of her round signal. Okay, so some wishy-washy real-world example is that Alice observes the entire stock market's performance, but she only tells Bob one stock's performance, and she picks which one she's going to tell him strategically. Then Bob shouldn't necessarily believe that everything Alice knows is represented by this one report. She might have told him the one outlier stock or something. Okay, and the definition I gave you before doesn't account for this, right? So the problem is that it's only talking about if I add a signal, what's the whole marginal value of adding that signal? If I take a signal away, what's the difference in value? Okay, so it doesn't account for this idea that I could add part of a signal. Clear so far? Okay. So here's a sort of pragmatic solution. Imagine that this marginal signal that we're adding, instead of adding the whole signal yi, we're going to add some randomized function of it, which economists like to call a garbling of the signal. Okay, right? Because that could just be I turn it into complete noise. It could be I reveal the whole signal, and it could be something in between. So this is sort of the space of all strategies that an agent holding yi might have in what they reveal. And we'll say these signals, we'll define them to be strong substitutes if, starting from any subset of the other signals, this marginal value of this randomized garbling is still diminishing in how much you know. Okay, so an example of a garbling could just be, Alice knows the exact temperature reading, but she chooses to add Gaussian noise with some variance. Okay, and if that variance is really, really high, then she's basically telling nothing about the temperature. And as the variance gets lower and lower, she's revealing more and more information about the temperature. So those are all possible garblings of the temperature. And it should be the case that for all of those, the marginal value of that piece of information is diminishing in how much you know of everything else. Okay, and I'm using this notation, A join, something to mean that I observe both the signals in A and the something else, the signal, the additional signal. So I'm thinking of this as a join signal, a join symbol. Is this okay? I'm seeing some faces that might look confused or bothered. It's kind of hard to tell. Okay. So yeah, again, the intuition I want to capture is that if Alice is strategically revealing not just her whole signal, but some randomized function of it, she's still getting this diminishing marginal value for her signal.
Is there a formal definition of like randomized function? Like you gave an example of adding white noise.
Yes. Okay. Good. So, so to keep things simple, we want to just focus in our paper on the signals like yi has a finite set of outcomes, and we're formalizing randomization as well. Actually, I was kind of thinking I don't really have time to get into it. So in economics, there's a way of modeling signals via partitions of a state space, and nature is picking at random an element of the state space, and which member of your partition you're in determines your signal. And if we extend this with some randomness, then we can use that to model randomized signals or garblings of signals. It's probably formalizable in a continuous way that is maybe even cleaner and doesn't talk about state spaces, but I'm not sure. You might, because this state space model is kind of like a measure theory type model, and you might have to use that to formalize this well. And actually that's something, yeah, I'm going to mention this next, I guess, that this is very, very closely related to what's called Blackwell's ordering or Blackwell's information criterion in statistics economics, which is a way of saying one signal is more informative than another. But Blackwell's kind of suffers some, it's not super mathematically convenient because, yeah, kind of because of this problem. Like there's such a big space of signals that there could be. But when we focus in on like what the signals Y tell us about X, it becomes more tractable and we can model it with the partition model easier. That probably didn't make a lot of sense, but I hope it gives some idea. Yeah, we're mainly thinking of finite outcome. And for modeling randomness, it's easiest to just think of like, take an arbitrarily small epsilon and the randomness is like from a set of size 1 over epsilon. Yeah, otherwise you seem to need measure theory that I don't want to deal with. So yeah, so the context related to what I was just talking about is you can kind of think of this as happening on lattices of signals. So what is a lattice? A lattice is a set that's partially ordered. And if you take two things in the set, they have some meet. And if they also have some join that is in the set. So here I've tried to draw a lattice where points are elements. And on the far left side, I have the bottom element that is less than everything. And on the far right side, I have the top element that's greater than everything. So this is a partial order. And they're ordered by informativeness. So these signals are ordered by how much these signals tell you about X, basically. For example, if this guy has a signal, this guy has a signal, then here's their join. So this point represents observing both of those signals together. And this is their meet, which represents sort of observing the common knowledge between those signals, which is formalized by Ullman in this partition model, but a little bit too far afield for me to define that model. Okay, so an example of a lattice is the subsets lattice, where points here are sets of signals, and the join operation is union. So I observe the union of this set and of this set. So like if this guy had a set of signals, this guy had a set of signals, this point is the union of theirs. I observe all of those. And the meet is their intersection. So I observe only what's common knowledge to both of them. And so then you can make a signal lattice which is much more fine-grained, and where these points are randomized functions of signals, and formalized in the partitions. And I'm sorry to not give you like the formal definition. This is all kind of background before we actually give results. So I want to get to the results, but I hope that gives an idea of what kind of what we're trying to say. So the big takeaway message is these discrete signals aren't quite good enough, and we have to deal with what if people are only revealing partial information. And you can do that by, again, this definition is sort of saying, okay, even if they take some signal that is on the signal lattice but less informative, you still have diminishing marginal value. So it's kind of extending submodularity a bit to this bigger lattice. But it's not quite the same as saying submodular over the entire lattice, which seems a little too strong for our applications. But yeah, and so this definition that I gave you, this is one way to extend substitutes definition to deal with this issue of strategically revealing partial information. And you could think of others, but I think all of them will use this idea that you have some lattice, some partial ordering of signals, and this is sort of the key idea that you want to use, diminishing marginal value over this partial order. Okay, I apologize if that's confusing or not enough detail. I guess I should tell you what our results are, though. So I'm going to keep going, or have a little time for people to formulate questions, and then keep going. Okay, so I claimed in the beginning, oh, substitutable items are so useful for markets and they're useful for algorithms. So I want to argue now that there seems hope that informational substitutes have similar applications or uses. Okay, so prediction markets. I want to think about prediction markets for you in this talk as a very simple game theoretic model that we should be able to solve. We should be able to find equilibria for, and actually have seemed pretty hard. Okay, so I'm not going to be worrying much about applications or claim that this is useful for the real world. I just want to talk about game theory. So the idea is, okay, I have a bunch of agents with signals yi's, and those are all informative about this event x, and I really want to get a good prediction for x. So I want some market mechanism that will maybe reward them for helping me aggregate information into a good prediction. And in a prediction market, these agents will come, for simplicity, one at a time to the mechanism. They're going to have some interaction where they make some prediction or they say something to the mechanism that I'll define for you. And they can maybe come back multiple times and update what they say later. And this will, the mechanism will aggregate these things into predictions and also assign monetary payoffs, eventually based on what outcome actually occurs. Okay, so I'll define it basically by induction. And this prediction market mechanism I'm going to describe to you is sort of proposed by Hansen. And it's not going to look like a market in terms of buying and selling shares, but you can actually formulate it that way without loss of generality. And that's a really cool connection I won't get into. So, so if you just had one participant, this market would be a proper scoring rule. Okay, they come, they make a prediction. You wait and see what the event is, and you pay them with this proper scoring rule, which we know is truthful. For example, the log scoring rule or any other. For a second participant, you're going to use a chained proper scoring rule, or what we call market scoring rule. They make a prediction R, and their payment is going to be the marginal improvement in score. Okay, so the score of their prediction minus the score of the first player's prediction. Okay, and if you just have two participants and they each arrive once, this is again truthful. Why? Well, it's truthful for the first player. They face a proper scoring rule. It's truthful for the second player because their utility is a proper scoring rule minus some amount of money they can't control. Right? This only depends on what the previous person said. And player 2 cannot control that. Okay, so player 2 says, okay, I'm going to have to pay out something. I'm going to lose something. But what I gain is a proper scoring rule, and so I want to be truthful as well. Okay, so this two-player game, if you understand proper scoring rules, which we've understood them for many, many years, is very simple, like very trivial. The equilibrium is they're both truthful, and that's it. So we're going to make a very small change, which is not even to introduce a third participant. We're just going to let the first participant come back and play again. Okay, so they can again make a prediction, and then they'll get paid by the marginal improvement of this prediction over the previous one. Okay, and so you can imagine in general for prediction markets, people are coming and every single time they get a marginal improvement in score. Right, but let's just try to analyze this three-player game. It actually becomes pretty hard. The reason is that the first player can make a lot of money if they can convince the middle person to make a dumb prediction. Okay, so if the first player can say something that misleads the second player into making a really bad prediction, then the first player will come back and they'll get a really good marginal amount here. Right, because they're getting their score of their truthful prediction minus some really bad score because this player was misled. And so we actually, I mean, there's been a few papers on this problem, and we only understand sort of very special cases of what does the equilibrium look like, and how does it depend on the scoring rule you choose, and how does it depend on the information that each of these agents have, so the yi's and the x. Okay, so what was known is that people had only studied the log scoring rule, which is the one I described to you. I mean, it's the best one, but it's the only one that was studied for this problem. And if the y's are conditionally independent on x, it was actually shown that in this game, you get this rushing behavior where the first player is truthful, so they're rushing to be truthful and say everything they know. The second player will do a Bayesian update on that and be truthful, conditioned on both their information, so their information is aggregated. And then the first player doesn't have anything more to say, and so they don't need to even participate. Okay, so this was proven in this paper, and then they extended it to show this result extends to show in any prediction market, if you have this information structure, you get this awesome result where everyone rushes and they're all truthful at the beginning. Okay, and information's aggregated as quickly as possible. So it's a sort of best of all possible worlds. And then this paper eventually was able to show that if the signals are unconditionally independent, you get this opposite effect. So let me make sure I distinguish these two. So this one could be, let's say x is a real number again, and then all the y's are normally distributed with mean x independently. Then those are conditionally independent on x. But unconditionally independent would be something like, first all the y's are drawn randomly, and then x is equal to their sum or something. So they're just unconditionally independent. And those two scenarios might not sound that different to you, but these papers show they're completely opposite. So this delay behavior is the first player will say nothing on day one. The second player comes and is truthful, and then the first player comes and is finally truthful on day 3 in this drawing I had back here. So they say nothing, this person's truthful, and then this person's truthful. So you get this maximally delayed, and they extend this to all prediction markets. Okay, and that's all that was known. Oh yeah, sorry, I'm getting pretty late, but that's all that we had. So in this paper, we sort of say, okay, we can at least characterize this these two types of behavior with substitutes and complements. So if and only if the signals are strong substitutes, so including this possibility of partially revealing signals, if they're substitutes according to that definition, the only equilibria are these all rush equilibria, which are great, where everyone is truthful as soon as possible and information is immediately aggregated. So there's this idea of the efficient market hypothesis, and for these very limited toy models of markets, we're saying that hypothesis corresponds to substitutes. Information is immediately aggregated if and only if it substitutes. And then if they're complements, you get this opposite thing. And the intuition is really straightforward. In the proofs, you have to worry about things like perfect Bayesian equilibrium versus Bayes-Nash and so on, but the intuition is really straightforward. It's that, okay, when I say substitutes, I mean substitutes relative to this scoring rule that was chosen by the market designer. Okay, and the payment here by design is really the marginal value of information. So the expected payment I get is when I make some prediction is really the marginal value as measured by this proper scoring rule over the previous information that was there. Okay, and this really is kind of straightforward from this. If you take expectations, you get expected utility sort of thing. You can take my word for it. So substitutes means diminishing marginal value, and it means that if I wait, then I'm only going to be expecting to get less. And this sort of argument shows that in equilibrium, people are rushing. And that's all I wanted to say about the proof. Okay, so let me, I don't want to run over. So let me just summarize quickly this idea of the algorithms. Well, no, I should wait. I should ask for questions though. And yeah, again, I'm hoping more to just give you an idea of these sort of ideas in this area of research that is probably different from what you're used to. So, it doesn't really bother me to not finish, but if you're confused about something, okay. So I think I can finish close to on time. So the algorithmic question that we're formalizing is, okay, I have a utility function. I'm one of these agents who has to act. And I know the joint distribution over all these signals, but I don't have access to these signals unless I pay the price. Okay, so I have a budget constraint, for example. So I can buy up to $100 worth of signals. Which signals should I acquire to fit in my budget constraint? Okay, so for example, I really care about the weather outcome, and these are different weather forecasts, but I have to pay to get them. Okay, so we just want to know what's the complexity of that problem. The challenge or annoying thing is that like this joint distribution could be exponentially large in the number of signals. The utility function could be computationally hard to optimize. And previous work on these sorts of problems have really focused on these aspects of it. So how do I represent a joint distribution concisely and such things? And we're just saying, okay, if these are given as an oracle for you and it's easy, what's the complexity? And of course, it's sort of directly connected to submodular maximization. So just by applying submodular maximization, essentially, together with the oracles, we can get a 1 minus 1 over e approximation to this problem in polynomial time if those signals were substitutes. Okay, and if they're complements or in general, we can't guarantee such an approximation with the polynomial number of queries. And this isn't totally trivial. This is the least trivial proof in the paper because you have to do a reduction from set function maximization to these utility function problems. Okay, good. So it's probably time, right? Yeah, okay, good. So what was this shadow slide supposed to be? The point is that this paper gives a lot of results about the shadows that are cast by substitutes and complements. So these are the shapes that they make, but it doesn't talk a lot about substitutes and complements themselves. So what do we know about these objects? So we have a few examples. Just skimming. I tried to argue that we have some intuition in geometry, which says for example, if I'm running a market and I want to create substitutability, how should I design my market? And I'm arguing that the pictures I drew for you can go some way to answering those questions. And with some other, I'm trying to finish up some of these other applications, and then so I can post the paper online. Okay, so it's more a paper about future possibilities than about what we've proven so far. And there's some open problems and some places you can read more, and I'll stop there. Thanks very much.
Thank you, Bill.
No. Okay, so if you want to stay and ask questions, that's great. And of course, I'm also reachable via email, whatever.
Do we have any more questions? Okay, so we can stay around for, we'll go offline now, but before we do, just a reminder that 2 weeks from now we have Mark Sandry, and 4 weeks from now we have Jerry Lee. So we'll see you then. Thank you for joining us. So I'll take this off air now.